In this video, we're going to discuss the acid-base properties of various compounds. This table gives you the names and chemical formulas of a number of commonly encountered acids and bases. For the acids, you can notice that all of the formulas start with H. This is usually an indication that you're dealing with an acid of some sort. This is the ionizable hydrogen. In the case of organic acids, such as acetic acid, there might be additional hydrogen atoms which are possibly attached to carbon atoms which are not ionizable. So you see here that acetic acid has a single ionizable hydrogen atom. Aspirin likewise has only just one of its 8 hydrogens that acts as an acid. We can also notice that there are also inorganic acids, things like hydrochloric acid. This is a compound that is used in the digestive process for breaking down proteins in your stomach. And likewise, sulfuric acid, H2SO4. In this case, there are 2 ionizable hydrogens in that formula. For the bases, commonly the second ion present in the formula is a hydroxide, as you can see for something like sodium hydroxide or calcium hydroxide. However, one exception to this is ammonia. If you take and dissolve ammonia in water, it actually acts as a base, but there doesn't appear to be any hydroxide in the formula. We will discuss this in detail. In terms of whether a compound is an acid or not, typically the ability to have the hydrogen come off and form H plus is determined by the polarity of the bond that it might form with some other element. So if there is a large difference in electronegativity between the hydrogen and, say, some other atom, there's a high likelihood that that will act as an acid. It turns out that a good example of an acid is something like nitrous acid. In this particular case, there's one ionizable hydrogen, and when this dissociates, it breaks up into H plus and NO2 minus. This happens to be a weak acid, and so we write this as an equilibrium. And of course, we do not break up the polyatomic ion nitrite. As another example, you could have a binary acid where there are only 2 elements in the formula, hydrogen and then some anion of some sort. In this case, we have hydrogen sulfide, which when dissolved in water produces hydrogen ions and the anion sulfide. This is also a weak acid and doesn't completely dissociate and establishes the equilibrium that you see here. At this point, we should discuss how to go about naming various acids. To do this, we first have to be able to identify the anion that is in the formula. Typically, if we're dealing with an oxo acid, in this particular case, the anions are going to be a polyatomic ion. These polyatomic ions could end with the suffix "ate" or possibly "ite," depending upon how many oxygens there are. In the name for the acid itself, we replace the suffix "ate" or "ite" with the suffixes "us" or "ic." So the corresponding "ite" ion will produce an "us" acid, and an "ate" ion would produce an "ic" acid. So, as an example of this, if we have the anion SO4 2-, which is sulfate, the corresponding acid is H2SO4, which is sulfuric acid, by replacing the 8 with the ic acid. So, The crucial thing is that in this case, the sulfur-containing compounds are going to have the possibility of being ate or possibly ite, so there's a sulfurous acid as well. Likewise, there's phosphate and phosphite, so we could have phosphorus acid or phosphoric acid. If we have a binary acid, in other words, there's only a single atom in the anion, this is quite common for things like the halogens. The corresponding acids are named by replacing the suffix "ide" with the prefix of hydro and then a suffix of "ic" and acid. So, as an example of this, if I have the chloride ion, we would have a compound that is an acid, which would have the formula HCl. In the gas phase, this is known as hydrogen chloride because it's a binary molecular compound. It acts like a molecular compound in the gas phase. But when dissolved in water, it acts as an acid. And so in this case, since we have AQ after the formula, as you see on the right, the name would be hydrochloric acid. In the case of fluoride, the formula of the acid would be HF. In the gas phase, we would name it following the molecular naming rules. So this would be hydrogen fluoride. But when dissolved in water, it acts as an acid, so we name it as hydrofluoric acid. As an example of how to take the name and figure out what the formula of the compound is, in this case we have the name hydrobromic acid. In this particular case, it's asking what is the compound. Is it an ionic or a molecular compound? And in this particular case, we're dealing with the prefix hydro and the suffix ic acid. So this is telling us that it's an ionic compound dissolved in water, and it must contain hydrogen and bromine. The bromine is, in terms of its charge, going to be -1. So this is then combined with the H plus. And so in this case, our formula is HBr and AQ. As another example, if we ask what's the formula of chlorous acid, in this particular case, we gotta first ask ourselves, is this an ionic or molecular compound? Well, since we've named it as an acid, it's going to be an aqueous solution, and it's going to be an ionic compound. So in this particular case, it's going to have the suffix of "us." So that means that we have to figure out what the ion is, and in this case, the cation is H plus, but the anion, in this case, is chlorous acid. And so we have to have the corresponding ite ending for the anion. And of course, chlorite, because you've memorized your polyatomic ions, chlorite has the formula of ClO2 with a -1 charge. So if we combine H plus with ClO2 -1, we then come up with the formula of HClO2, which is dissolved in aqueous solution. It turns out that in some cases, certain polyatomic anions can have varying numbers of hydrogens associated with them, and these are referred to as polyprotic acids. And so there can be a varying number of hydrogens associated with this polyatomic ion. A good example of this is the phosphate ion, which we know from our polyatomic ions is PO4 with a 3- charge. However, if we start giving the hydrogen ion to the phosphate, we could produce two other ions. The first is to give one H plus to the PO43 minus. This provides the compound that we call the monohydrogen phosphate ion. You'll notice that the negative charge of this ion has gone down by 1 in comparison to phosphate. If you give two hydrogen ions to phosphate, you would have the dihydrogen phosphate ion, which only is -1. Likewise, if we had sulfate is SO42 minus, we can give one hydrogen ion and produce the so-called hydrogen sulfate ion. It turns out that acids and bases produce solutions which are either acidic or basic, and oftentimes we can have compounds that produce different colors depending upon whether or not the solution is acidic or basic. These are referred to as indicators, and they are extremely useful for identifying whether a compound is an acid base or possibly a neutral compound. So, if we were to take this colored compound, sometimes referred to as a dye, and put it in solutions with various amounts of acids or bases, we might end up with the different colors that you might see here. So, a really good, useful indicator is anthocyanin. It's the color that comes from cabbage, and it's a fairly complex organic molecule, but indeed is very sensitive. Its color is very sensitive to whether or not the hydrogen ions interact with that molecule or not.